Okay, so in today's class, we will continue our discussion from last lesson where we talked about the concepts of stability. We looked at the stability criteria. We looked at the basic concepts of controllability. So we actually talked about the dynamical system equations and then what these equations mean in terms of stability about an equilibrium point or stability about a periodic solution. We looked at the mathematical definitions of stability, but the most important part here is to understand the physics. So what does it mean when we talk about if a system is stable or unstable? And then we looked at these simple equations, and these equations we tried to implement on Mambo platform. Now, I just want to give you some ideas here what this means when we talk about the implementation. So when we talk about the implementation of these equations, I want you to understand that this equation is nothing but T is equal to I times alpha. This is what this second equation is. And the first equation is simply stating when the two coordinate systems are aligned, when the northeast down coordinate system of the Mambo, northeast down coordinate system of Mambo is aligned with the inertial coordinate frame, the body rates, so roll rate, pitch rate, yaw rate, so the body rates are equal to inertial rates. What that means is the transformation matrix that takes from body to inertial coordinate frame is identity. That's what it means. And this is true for a simple hover. So when we are trying to design a controller for simple hover, we can make this assumption like the inertial coordinate frame is aligned with the body coordinate frame, and the body rate, pitch rate, roll rate, and yaw rate are same as the inertial rates. And that equation will be used when we actually implement the hover controller. So imagine if I want to design the controller for hover without looking at the dynamics. So here is a simple idea. If for some reason aircraft is pitching down, what I want to do is I want to increase the speeds of front two rotors and decrease the speed of back two rotors. So clearly my hope is when it is pitching down, it will be in a level flight. Same argument when it is rolling, when it rolls, at that time I want these two rotors to speed up and I want these two rotors to speed down. And a simple proportional controller would increase or decrease the speeds of the motor depending upon the pitch or the roll. If it has more pitch, it will actually increase the speeds more. If it has less pitch, it would increase the speed less. But that is possible. Imagine the aircraft is pitching down. You increase the speed, but it may not go to the level flight. It can go up. And then you want to decrease the speed, so it will go down. So you would observe some sort of pendulum type motion in this dynamics. Same thing, you'll see the roll type motion, sort of a pendulum type motion in the dynamics. But once you add the derivative control, once you add the integral control, what essentially you are doing is you are converting. This is super duper important, so please pay attention. What you are doing is initially you have some sort of undamped pendulum. You are making that pendulum more and more damped. So as you increase the derivative gain, you'd observe that the pendulum oscillations would be dampened. But then you will notice that you are going to have a steady state offset. For that, you would do an integral control, and then basically just making sure that integral does not wind up. Then you can actually have a very stable control. So that is the common sense logic behind controlling the drone in the roll and in the pitch. So clearly we need some estimation of roll and pitch angle when we decide to control the drone. Now, next part is a little bit math coming at you. So the idea is we are going to assume some type of an energy function, that describes the dynamics. If the total energy is remaining constant as the time goes on, the system is said to be in neutral equilibrium, or it's in just stable equilibrium. If the energy decreases over the period of time, then the system eventually has to come to rest. And that means the system is in asymptotic stability. If the energy continues to increase, then the system is unstable. So our objective is that the total energy that is imparted because of the external disturbance should dissipate over the time and the system should become stable. So that is the key observation. So what we want is, and again, when you decide the stability, there are stability about the fixed point. The stability about the fixed point, which means it's in the level flight, and that is called as the trim condition. So aircraft is trimmed, which means aircraft is in steady state, level flight. Or you can have the stability about the periodic solution, which means the aircraft is going forward and backward, and then even if there is a disturbance, the aircraft continues to follow the set trajectory, and gradually the disturbance is minimized. And then next part is, there is this concept of controllability, and this concept is very important. So what does that mean? It means that you should be able to exercise some type of control on the state that you have some control over. So this needs a little discussion, and I will actually talk about this little bit in more detail. I mean, mathematics, the equation for mathematics and all that come later, but let me explain to you what controllability means. Controllability means ability to control. So for an example, when the kids are small, the parents have ability to control their behavior. The kids get older, as soon as they become teenagers, they become rebellious, and all of a sudden the parents' control authority drops down. Same thing happens with controllability in the case of a system. So what I want you to understand is, you have, say, we have a dynamical system. So for an example, we have a dynamical system, and this is sort of the mass, and this is traveling in a straight line. We have x and x dot. So if I use the Newton's equation, force is equal to mass times acceleration. Force is sort of the control, that external control that is changing system state. Now I'm going to write this equation down in state space. So this equation is the second order equation, which is force is equal to mass times x double dot. I'm going to consider the two states variables, x as displacement and x dot as velocity. So what I want to do is I want to convert this second order differential equation into set of two first order differential equations. So this is what I'm going to do. X dot d by dt is equal to, I'm going to have this matrix here. So please understand, my states are again x dot dt x is nothing but x dot. So this becomes 0, 1, and x double dot is equal to 1. So I'll have to write this down. X double dot is equal to f divided by m. X double dot is equal to 0 f by m. So now I want you to look at this equation. When you expand this equation, you are going to have dx by dt is equal to x dot, and d by dt of x dot is equal to f divided by m. Are you with me so far? So this second order equation got converted into two first order set of equations. Now, if I want to rewrite this equation as something like, and I want you to notice this, this is a standard form, x dot is equal to ax plus bu, where u is the external force. This equation will be written as where u is equal to f divided by m. Now, so this simple dynamical system, which is the mass under the Newton's second law, force is equal to mass times acceleration, can be expressed as the first order system. And now I want to investigate something called as the controllability of this system. So controllability of the system is nothing but what you do is, and you construct something called as a controllability matrix. So controllability matrix is the vector B, then the product of matrix A times vector B, and you would continue doing that till you have A to the power basically 0, which becomes identity, and you find out the overall rank. So what's going to happen is, so I want you to look at this. So in our case, I will write this over here. In our case, controllability matrix is given as B, A, B, A, n minus 1, B. So let's see the number of states here, n is equal to 2. So what I'm going to do is I will have B, then A, B. So B is 0, 1. A is 0, 0, 1, 0. So let me write this down here. 1, 0. So A times B is 0, 0, 1, 0, 0, 1. So this becomes first row, first column, second row, first column. So this will become 1, 0. And now I have to find out the rank of this. Now, what is rank? Rank is number of independent rows or columns. Now, what does this mean? Please observe that if you use MATLAB and find the value of rank, say rank 0, 1, semicolon 1, 0, what would you get? Get 2. Why would you get rank 2? What that means is the first column is independent of second column. So first column is independent of second column. What that means, I want you to understand, if I consider 0, 1 as a vector, then please note I have 0, 1. I have this vector 0, 1. And when I consider 1, 0 as a vector, I have 1, 0. And this is 0, 1. And you can see that these two vectors are perpendicular to each other, which means they are independent of each other, which means the rank is equal to 2, which means this matrix, controllability matrix, has the full rank. What does that mean? This is what it means. It means by changing the magnitude of force, you can control the velocity and you can control the displacement. Everyone understood this? Controllability means that whatever external function that you have is able to influence all the states that are inside the system. So here, if I change the value of control, if I make control is equal to 0, you agree with me? If my control is 0, my velocity is going to be 0. Clearly, my displacement is going to be 0. If my control is sinusoidal, if it is going back and forth, clearly that sinusoidal control would influence the velocity, and since the integration of velocity is displacement, it will also influence the displacement. Everyone understood this? So controllability means that whatever external function that I have, u is able to influence x and x dot. Do you agree with me? Now I want to make this problem slightly different, and I want to tell you that there is angular acceleration, or maybe instead of this just going forward and backward, maybe what I have is this is in 2 dimensions, and it can go forward, and this can also rotate. If I go forward, and this can also rotate. Now, please try to understand, if I add this additional state, so let me write the equation for this guy. So insert So let me add this slide. So what I have now is I have x, I have x dot, I have theta, and I have theta dot. X d by dt is equal to x dot theta dot, and the equations that I'm looking at are f is equal to ma and t is equal to I alpha. For the sake of discussion, let me assume m is equal to 1, I is equal to 1. And then I'm going to have a vector here. And then I'm going to have maybe some u. So what I'm going to do is I'm going to write this equation down. I'm going to say this is x 0 1 0 0 0 0 0 0 1 0. Here same thing, 0, this is theta, by the way, this is theta, 0 0 1 0 0 0 0 0. Now ideally, okay, a step back. Ideally what I want to do is I want to write this equation down something like 0 f 0 t. Are you with me so far? Everyone understood? So I have, now what I have done is I have this mass can translate, but in addition, this mass can oscillate about the z-axis. So it can rotate and it can travel. So basically, this can go like this can go like this can go like this. And this is my external vector. Yeah.
So why can't we modify this matrix such that it divides the column and multiplies by r rather than writing it in column?
Oh, because what I want to do is I want to write this entire system as x dot is equal to ax plus bu.
Okay, bu.
But hold on a second. There is something else going on here that I haven't explained completely. Now, x dot is equal to ax plus bu. B is a vector and u is a function. Let me repeat. A is a matrix, x is a vector, b is a vector, and u is a function. Now, I'm going to make a small adjustment to this equation. I'm going to say something like this. And I'm going to rewrite this whole guy, and it's very important. Please note, I'm going to rewrite this whole guy as 0 1 0 0 and maybe f or u, something like this. Do you agree with me?
Shouldn't it be tau?
I said that there is no tau on this. So let me explain it to you in just a second what I mean by that, and it will clearly make my point. So you have this object. This object can translate back and forth, and also it can rotate left and right. Do you agree with me? And here, the equation that I really want to implement is f is equal to m times a, t is equal to I times alpha. But what I'm going to do is I'm going to deliberately set capital T is equal to 0. I'm going to deliberately set capital T is equal to 0, which means now my B matrix, B vector is 0, 1, 0, 0, and my matrix A is going to be whatever I have over here. And now if I construct the controllability matrix, my states n is equal to 4. If I say C, A comma B, they're gonna look like B, A B, A square B, and A cube B. And I would encourage you to work this problem, and you will realize that the rank will be less than 4, and which is quite logical, because if you want to control the angular motion of that mass, just the force in the horizontal direction won't help you control the angular motion of the mass. In other words, that angular state, angle and angular velocity are not controllable by the horizontal force that is being applied onto this mass. Everyone understood this? I would encourage you to do this exercise. What I'm trying to say here is that the states, so think about, you have external force. External force is influencing one state of the system. That state somehow should be related to the other state in the system. Only then this external force indirectly can control the other state in the system. Do you agree with me? That is what is controllability. Once again, say the system has 10 states. Out of those 10 states, only one state is directly related to the external force or other torque. But all 9 states are related to each other, and they are somehow related to the first state. What that means is that external force somehow is going to flow through this entire system and control all the states. If there is no coupling, if there is no link between those internal states of the system, that state is not controllable because of the external force. Everyone understood this? Because external force cannot reach, external force cannot influence that state. And that is the meaning of controllability. That is what it means physically. Everyone understood this? And that's what, and again, if you want to look at the definition of controllability in terms of the vector that we talked about, what that means is 0, 1 and 1, 0. It tells you the domain of application of that external function. And in this particular case, that domain of application covers the entire plane, XY plane, which is called as the state space. That's why this system is controllable. And in the other case, the system is not controllable because that external force cannot influence some of the states in the system. Everyone understood this?
Okay, but how can we design something else?
Okay, so that is what you mean by that. That is when you have underactuated system. And classic example for underactuated system is Mambo or quadcopter. So what you do is you induce a coupling. You induce a coupling between the states, and that way you can influence the other state. And I'll tell you that in just a second what it means. So in other words, you design the controller in such a way that the controller would have either the physical or a virtual interaction with the states that initially were not controlled. Only then you can have the controllability. What does that mean in physical form? So this quadcopter has 6 degrees of freedom. There are 4 props. You can only control 4 states. In other words, This quadcopter, just by changing the speeds, cannot go forward, cannot go sideways. So what you do, you deliberately, you tilt the quadcopter. Initially, what that means is you induce a coupling between the forward state or the state X state, and then have that quadcopter go forward. Same thing happens when going towards right. What you do is you pitch this a little bit or roll this a little bit. That way you induce a coupling between the external forcing function and the translation motion, and then it can go like that. When it is in level flight, no matter what you do, you cannot make this quadcopter go forward or sideways. If you want this quadcopter to go forward, you will have to pitch it down or pitch it up, and only then it can go forward and backward. That is where the mixing algorithm comes in the picture. Everyone understood this? So controllability means you are trying to influence all the states of the system by external torque or force. If the external force or torque cannot reach some state, you change the dynamics. You add a coupling so that that external force or torque can somehow influence that hidden state, and only then you can control. That is actually called the underactuated systems, and there is a lot of stuff in there. So what I want to do is, next part, again there is, so let me talk about the conclusion. In this lesson we talked about controllability, and I don't know, probably some of you might have taken linear systems class, some of you might have taken state space class, and that is where they talk about controllability and observability, and you form the matrices and you find the rank. But at the end, this is what it means. Observability means you should be able to know what is happening at that state. So somehow you should be able to measure or observe. You can observe directly or you can observe indirectly. That's what means by observability. Controllability means by external forcing function, you should be able to influence that state. If you can't influence that state, basically you do not have any control. So that is what it means by controllability. And that rank condition talks about the independence, and it essentially says that if the control function is able to control the entire state space or just part of the state space. Next part is the low level flight control. I want to give you sort of a broad overview of what the low level flight control is. But again, let me emphasize, unless you do this programming by hand on the Mambo or any other platform, you will not realize how these things, how these algorithms that we talk about are implemented in actual practice. This is not a spectator sport. That's why please take those short assignments seriously and try to implement those algorithms and those logics on the Mambo. That will give you a better understanding of the control. So what are we going to do? So there is something called as, we have to understand when we talk about the low level control, what exactly are we controlling? So when we try to control, it is almost impossible to control a super complicated 6 degree of freedom dynamical system such as Mambo. So what we do is we make certain assumptions and we simplify, and we start with a simplified model and we implement position control, altitude control, etc. And depending upon the control laws that we want to implement, we come up with some sort of an algorithm, and that is called as control allocation. And then that control allocation results into some low level hardware programming, which is for the motor control. And you can verify all this logic using some sort of simulation algorithm or some sort of simulator that either we have created or that is given inside the MATLAB. So what I want to do is, first, let me talk about the overall flow of the control. How does control work? In the context of quadcopter, the first control that you are going to implement is the control of attitude. Attitude means roll, pitch, and yaw. Typically, we are not worried about yaw at this point. What I want is, I want this Mambo to be hovering steadily at one point. So clearly, when Mambo is pitching down, front two rotors to speed up. When the Mambo is rolling left or right, appropriate rotors should speed up and slow down. And what is going to cause these rotors to speed up and slow down? The PWM that is supplied to these motors would be changing. That would change the speed of those motors. Now, each motor would have its thrust coefficient. Each motor will have its torque coefficients. So basically, those thrust coefficients and torque coefficients would tell us what is the approximate speed variation that our controller should achieve. So please understand, there is always something called as the inner loop. Inner loop consists of altitude stabilization, always for quadcopters. You can't have, you first and foremost, you want to stabilize the altitude, which means the pitch and roll. Once this is stabilized, then you would want this quadcopter to follow a particular trajectory or particular path. So you want this quadcopter to go forward by some amount, by delta x. So what you will do is, here is how you will do it. You have acceleration measurement in the x direction, y direction, and z direction. You can doubly integrate acceleration and get displacement, but that is going to be super duper noisy. So how would you get an estimate of movement using the data from the optical flow camera? So what this camera would do is, it's going to take pictures all the time. It's going to do something called as digital image correlation, which is called DIC, and it will tell you how far the Mambo has moved forward, left, or left positive, left negative. Now, what happens when the Mambo is going to go up and down? Again, you have an accelerometer in the z direction. You can doubly integrate the acceleration in the z direction. That will give you its height, so at altitude. And in addition to that, there is this ultrasonic sensor that will give you distance from the ground. So you would use, so this is how the basic control algorithm is going to look like. First, you will use a complementary filter, find out the roll and pitch, and stabilize the roll and pitch. Everyone understood this? That is the first step. Second, you will measure the height using the pressure sensor and the ultrasonic sensor and use that to stabilize altitude. Then you will find X and Y's from the optical flow camera. You'll find X and Y's from optical flow camera and try to navigate your Mambo to the desired X and desired Y. That is how the overall control algorithm would look like. So I'm going to give you this algorithm. So control logic. And this is a very simple logic. And you will notice it will work not very well. It will work only for a small duration. After some time, it will actually become unstable. So first, pitch and roll calculation using complementary filter. Attitude, which I mean by that is roll, pitch, stabilization, then altitude stabilization using pressure sensor and ultrasonic sensor. So let me write this down. Theta and phi using complementary filter. Here you will find Z using complementary filter. And then you can just use proportion control. Initially, here you can use the proportion control. Then next, you'll find X and Y using optical flow. And then stabilization using delta X and delta Y. So what this means is X current minus X set point will form the error, and you will have a control Kp times error. This is Ex, Ey, Y current minus Y set point. So Kp Ey. And then the motor mixing algorithm would actually map which motors to speed up and slow down. Everyone understood the basic algorithm? Now I'm going to show you how it is implemented in MATLAB. So let me open MATLAB. So I want you to open Parrot getting started. And big and bulky MATLAB opens. So I want you so what I have done is I have implemented the complementary filter inside a MATLAB function. So this MATLAB function is called complementary filter data. And if you double click on this function, so let me start. It is so this complementary this function is grabbing ddx, which is the acceleration in the x direction, and it is capturing it should be capturing q. So it should be capturing q. So acceleration in x direction is this. Q is the roll gyro, the pitch gyro. If you double click on this MATLAB function, you will see that this complementary function, complementary filter is implemented as theta, which is the value of the pitch, which is computed based on the value of AX and the pitch angle, I mean the pitch gyro output Q. So what you have is theta is AX, A sine, AX divided by 9.81, and theta G is whatever is the pitch rate that you are getting multiplied by the update rate. Please note, the Mambo via Bluetooth is transmitting data at 20 Hertz, which means every sample is 1 divided by 20 seconds. So what I'm doing is I'm getting the value of the gyro rate, multiplying that by the time delta t, and that is getting me the angle. And at the end, what I'm doing is I'm implementing a very simple complementary filter. And in my complementary filter, the weight on the gyro angle is very small and weight on the acceleration is very large. That means I'm doing a gyro through high pass filtering and the accelerometer through a low pass filtering. So everyone understood this code? And then this code gets implemented here. So now I want to take this moment to implement the roll. Can someone tell me the equation for roll? What is the equation for roll? What is the equation for roll? A sine AY divided by 9.81 multiplied by cos theta. There is a minus sign here, right? Okay, so this is the angle from accelerometer, and from the gyro is P multiplied by delta T, and the complementary filter is going to be 0.05 0.95 So now I'm going to implement this code. So go to simulation, go to library browser, go to user defined functions, and then in user defined functions, you have this MATLAB function. Grab this MATLAB function, paste it over here, and this MATLAB function would have following inputs. It should have the value of theta. Then it should have the value of ddy. So I'm gonna say here function. I say cal c theta ay and p. C A is equal to A sine the parentheses AY divided by 9.81 divided by cosine theta. Phi g, yeah.
The theta which you are getting is in degrees.
No, I
No,
related.
from the previous one, the theta you multiplied by 18 and 9.81, right? Sorry, not 9.81, but 180 by pi, right?
I don't remember. Let me check. Is equal to 0.05 times g plus 0.95 times e. Save. Now,
You multiplied by 180 by pi.
okay, so what I would do is I'll just take this off from here. So now if you go to flight control, can you see there is one thing I need to change? I'm going to call this phi. And don't forget a negative sign here. And go to flight control system. And now I need to connect AY, which is DDY. And then P. Huh? Did I make a mistake?
Yeah, it's connected to
P is connected to P, right?
out is written below, right? Below the.
Okay, let me see. So first theta. Theta is connected to theta. AY is connected to DDY. DDZ? No. Oh, it connected to DDZ? Oh, yeah, you're right. So connected DVZ. That is not correct. AY should be connected. Should be connected DY.
It's connected to R, other one.
What?
And the other one is connected to R.
P, no.
Yeah, it's got
P, P, Q, and R.
they are getting from R.
R. Which nothing is connected to R.
In number 8, out number 8. Or is it connected to?
This should be connected to Q.
This one is connected to R.
And this should be connected to P.
R is connected to Q.
R is not connected to anything.
No, not PRS. Above that. Q, R. You mean pin number 8.
Okay.
Pin number 8. Out number 8.
Okay, so I'm okay. Hold on. Hold your horses. Okay. So theta is connected, correct. AY should be connected. Let me see. So this is DDX, DDY. Let me see, DDY. DDY is connected, AY. That is correct. Then DDZ is this. This is P. This is Q, right? This Q should be P should be this is P. No, this is not.
Out 6 is P. 6 is Q. 6 is P.
This is P. This is Q. So, okay. So this Q should be connected to Q here. Okay. And this P this P should be connected to P. Let me see where is P. Okay. Is this right? So let's see. P is connected to P. AY is AY, TDY is connected to AY. P is connected to P. So see here, P, and this guy should be connected to Q. Connect to Q. Okay. So with that, we are ready to program our Mambos. Wait. Patrick, hold your horses. First, let me get to these basic steps. Join the personal area network. Connect using access point. Connection successful. Build, deploy, and start. Oh, I forgot to add the scope. Yeah, so I made a mistake. I forgot to add the scope. So we can add the scope and do monitor and tune, and you should be able to get the output from the complementary filter. Simulation. Scope. Yeah. Yeah, you can do it. Totally fine. There are multiple ways of doing it. The reason I wanted to show you this is because implementing, if you use function, implementing the PID control is super simple. Otherwise, you'll have to create those blocks and do it, right? Now, what you can do is just go here inside and then add an error function and then actually connect this to mixing block, which is on top. Can you see that there is just, can you see this motor output block? So what this means, this PWM output, it's sent to 1 and 3, 2 and 4. So now you directly have access to 1, 2, 3 and 4. So okay, first, I think I'm a little bit going ahead of myself. But before I go there, let me ask my online students if there are any questions. Online students, everyone understood what I have done here? Any update questions from online students? So why did I use this block? Because what I want to show you in next few minutes that I have. If you think about it, when the quadcopter is in level flight, what is the set point? Set point is 0. Do you agree with me? Which means error is nothing but the angle of phi and theta, whatever angle I'm getting. Do you agree with me? So what I can do is, in this function itself, I can choose a suitable constant and connect this directly to the motor mixing block, which is on the top, and that will control the speed of the motors. Just a second. So, oh, it's not connected via Bluetooth. Someone else's Mambo online? So please try this. That way. Okay. Tatvik, is your Bluetooth on? Everyone's Bluetooth is off. So please turn off your Mambos. And use monitor and tune, because that runs the code in an external mode. In an external mode, you will get the data from the hardware. So online students, any questions? I'm looking at the chat window. If you have any questions, please ask quickly. Okay, now it will start. Start. And then you can see so you should be able to see scope 4 and scope 3, scope 2. Now check this out. And then the scope, can you see? I'm rolling. Roll. That is good. What? No, actually, the scale is off here, so I'll show you the scale. It will be about the same scale. And actually, the filtering is different. I think on roll, let me see. So I actually did heavy duty filtering on pitch, not so filtering on roll. So I'll show you what I did. So, and that's deliberate. So what I want you to do is, I want you to look at this complementary filter code. And can you see here it is 0.02 theta plus 0.98 theta. So 0.98 is on the acceleration and 0.02 is on the gyro. Now I want you to go to this guy. And can you see it is 0.05 and 0.95. So the weights are different. That's why the response is different. Everyone understood this? Now, how would you implement this into the stabilization algorithm? I just have 1 minute, but I'll show you how it, and please try this. So here you have this motor mixing algorithm. So if you look at the motor mixing algorithm, what you have is, you are actually generating the pulse width modulation. And for this pulse width modulation, you have control over amplitude, period, and pulse width. So what you can do is, you can vary the pulse width, and that will change the speed of the motors. And so what you will do is, the pulse width, which is over here, would be the input from your theta angle and phi angle. Everyone understood this? And that is how you would actually control the roll and pitch. I'm gonna stop here today. And if you have any questions, I would be happy to answer in next class. Huh? Last part. So this is the motor mixing algorithm. What is this motor mixing algorithm? This is the input to motor 1. Huh?
It's a controller for PWM.
Controller for PWM. So what you will do is, you will adjust the PWM, that will change the speed of the motors. And that change of PWM will be dependent on the error. So the pitch multiplied by a constant, that you will map it to PWM.
Okay.
So play with this block. This is the motor mixing block. And then you will notice that what should happen is, if it is pitches up or down, 2 motors should speed up, 2 motors should speed down. If it rolls and pitches, 2 motors should speed up, 2 motors should speed down. So, and try to run this and you will see that it will work.
Then what is that E theta?
Huh?
That E angle.
T? Which one?
You can know there is a E angle, current angle from minus. No, current angle minus that part.
Current angle is the angle that you get from the complementary filter. And set angle is when the aircraft is horizontal, the roll is 0, pitch is 0, set angle is 0. So I'm going to stop here.
Professor,
Yeah.
so this is for bar number, but when you, let's say you build a drone by yourself, and it would be the same procedure for that also?
Exact same procedure.
Same.
So you can talk to Tatvik. Tatvik is building his own drone from scratch. And if you really want to do this, I would be doing the same exercise. So in my mechatronics class, where I would actually start with a simple drone, we'll build drone from scratch. But idea is the same. Even advanced autopilot systems will run the PID loops. The only thing that we haven't discussed here is something called as the state flow. So I don't think I will have time to discuss the state flow, but state flow algorithm would actually tell you that how would you change states and how would you switch the algorithm depending upon different values of theta, phi, and motion.
So PIXOC also be
PIXOC does exactly the same thing.
Regarding the outline for the board.
Okay.
Which one?
All right. I will see you all next class.